My name is Zachary Geeraerts. I will be speaking about my attempt to model the catalytic decomposition of chlorite from chlorite dismutase. So, what is chlorite dismutase? Well, it is a heme B containing enzyme that catalyzes the unimolecular decomposition of chlorite to chloride and molecular oxygen. It is not to be confused with the disproportionation reaction of chloride, which is exemplified by these latter two reactions. It is very interesting because it is the only known enzymatic process, other than those in photosystems too, that actually catalyzes OO bond formation. So there is a little bit of interest. So what does it look like? Well, this is a three-dimensional pictorial diagram of what the protein backbone of chloride dismutase looks like. So in blue, I have what the chloride dismutase from a species known as Decomposition aromatica, soil-dwelling bacterium. In green, here this comes from Klebsiella pneumoniae. As you may know, due to pneumonia, can actually be a pathogen. So the idea here is that they are actually found across a wide range of gram-negative bacteria. And so on the far left there, I kind of show a picture diagram of what the pocket looks like and what the heme active site looks like. So we have our heme, our iron center that is actually ligated by a histidine, which coordinates it to the protein backbone. And there is an arginine residue that holds or hangs over the heme site, which actually is very important for catalysis. We're not going to get into that today. All right, so what is the whole goal of kind of this study of modeling this reaction? Well, we have a proposed mechanism based off of our current understanding of the system. And so what I'm showing you is effectively several steps. I have my resting step of my enzyme, then I have a state in which the substrate is bound, then I have what we think is a steady state intermediate buildup from other spectroscopic evidence, and then finally we have this rebound state, which is a peroxyhydrochloride form. And then we go to products. So, just to be clear, this looks very messy in a way, or I shouldn't say messy, it's very cluttered. But it's just to keep track of where the electrons are as this mechanism is going through. The thing to keep in mind is that this first state and this last state have not been observed. So they very well could be transition states instead of intermediates. The point is we do not know. However, the intermediate, known as compound 1, we are to some degree confident with. I will actually be trying to verify that this summer. So, anyways, so what is the method that I will be applying here? Well, I have used a dynamic wave packet Gaussian script in MATLAB, where I am attempting to model the decomposition of chlorite as the substrate approaches the catalytic center. And so the wave packet I have used here, my wave equation, is a Gaussian wave equation. It's strange, but notice how it is dependent on momentum. It will evolve in time by the time evolution operator, shown here as U, which has a Hamiltonian, which is dependent on both momentum for the kinetic energy portion and a time-dependent potential, which will be reflected by the potential energy associated with uncatalytic decomposition, V1, and the catalytic decomposition, V2. And so what I do is I take the linear combination of these two Morse potentials, is what I used. And I change their relative contributions to the overall potential with time. So I go from starting with predominantly by uncatalyzed potential and slowly build into my catalyzed potential. So how does that look? I will show you here in the next one. The thing to keep in mind is that I'm looking at the probability distribution of this wave packet as a function of time and position. So how am I determining my rates? Well, I'm looking at the probability of reaction by just integrating over half the box I have this confined into, and I'm determining my rates by the overall change of this probability divided by the probability change as a function of time. So, and then for the last little bit, since I'm looking at catalysis, looking at activation energies may be interesting. So I actually use the Arrhenius equation to kind of get an idea of how the activation energies are changing with the change in potentials. All right, so how does this look? Well, as you can see, on my x-axis, I want some position coordinate, and on my y-axis, this is the probability distribution of my wave packet. And as you can see, the green potential at the time is changing, right? And as it changes, if you remember from my equation, I'm saying the probability of reaction is half the box length, so in our case, about 75 or 60. As that probability distribution spills over onto the other side, I'm going to product this from my assumption. Okay, so what happens when I run this program? Interesting things that are not maybe relevant, but interesting things nonetheless. So what I've effectively done, if you recall, my wave packet was dependent on momentum, so was my Hamiltonian. Well, I'm getting negative rates. That would be okay if I could rationalize that negative rates means disappearance of substrate, that'd be fine. But if you look at what's happening when I'm increasing momentum and effectively increasing my kinetic energy, my rates are going down. So it's a little backwards. And I think that has something to do with how I'm determining my rates. Also, just to kind of set upper bound and lower bound limits. So this is just the linear convolution of those two potentials. I also looked at just with the uncatalyzed potential V1 and catalyzed potentials V2. So effectively, you would expect the uncatalyzed potentials to have slower rates, and the catalyzed potentials to have faster rates. Well, do I see that? Well, no. So my catalyzed rates, granted they are less negative, but they are still negative, whereas my uncatalyzed rates are generally speaking much higher. So there is clearly a problem with how I modeled this, but that can be figured out with time. All right, so what kind of results occur from this? Well, so this is just my uncatalyzed potential or probability distribution for the uncatalyzed potential that I used. And so, as you can see, on my y-axis, this is position. On the x-axis, I have time. And then z-axis, that's my probability distribution. And so with time, you can see it the wave packet changes based off of the time evolution operator, but its position doesn't really escape that well. Now, we've removed the barrier effectively with my catalyzed potential. And what happens? Well, my wave packet propagates all the way across to the box at the end of my dimensions, basically, and then I get an artificial reflection. So, in other words, I've ran my simulation longer than the box length. And so, yes, this would suggest, okay, we're going to products uninhibited, but we also get this back reflection that is not used. Now what happens when we combine them? Well, it looks very similar to the uncatalyzed potential. However, the difference is if you look at the spread, if you noticed from the uncatalyzed potential, that spread didn't go farther than around 20. I had this in angstroms from my position. However, with this linear combination, I am slowly moving towards products because my position has increased ever so slightly. So that makes sense to some degree. What about the activation energies? Right off the bat, this should scream to you something's wrong. I have positive slopes for my Arrhenius. Does not make sense. Well, it's because I had negative rates and I had an inverse correlation with momentum and the rate itself. However, so just to kind of get you on the same page, how I correlated temperature with momentum was through this expression, is that expression p squared, my momentum squared over 2m, that is for kinetic energy, and then using the ultimate constant, I can get temperature. And so that's where I get my temperatures, and I did that for every rate that I calculated, fit them to a line. This is the Arrhenius expression I used. However, I just determined my activation energies as the slope and not the negative slope. So I cheated a little bit. But the interesting thing is, this is my uncatalyzed line. This is the linear combination line, and this is the catalyzed line. Notice how the activation energies are dropping. So yes, I have cheated a little bit in switching the signs on my equation. But the trend is there, which is very good, because I can, if I figure out my inverse relationship problem, I can model the changes in activation energy with respect to the catalyzed and uncatalyzed potentials. Okay, so my conclusions overall are my model is incomplete due to those problems of having those inverse correlations between momentum and rates, as well as the potentials and rates. However, there is very strong promise that this will work, because I was able to model my activation energies somewhat convincingly. So what does one do after at this point? Well, I didn't tell you this, but the mass I used was the mass for an electron, not an actual nucleus. And that's because of how my parameters were set up. I wasn't quite able to optimize my simulation to incorporate a larger mass. So that would be the first thing. Next thing to do after, besides just fixing the rate problem, is incorporate actual potentials that correspond to the catalyzed reaction and the uncatalyzed reaction, based off of any potential energy surface diagrams that may be available for those reactions. Then, what would be fantastic is if I could predict measured rates, or rates that have been experimentally determined. And then, ideally, if you remember, harken back to my mechanism, I am just trying to model the overall reaction. The whole point would be, okay, if I can do that, can I model each individual step along the reaction path to try and gain insight on the energetics of that mechanism and hopefully figure out what it is. Questions?
Okay, I was joining thinking